Welcome everybody to the second part of lecture number 6. We'll be talking about the electric potential. In the previous lecture, lecture number 5, we talked about the fundamental laws that governs the electromagnetic field or the electrostatic field, and we said that the curl of E equals 0, and we explained that means that the electric field is a conservative field. So from the vector algebra, if the curl of a vector equals 0, so we can express this vector as a gradient of a scalar function. So because curl E equals 0, we can express E as a gradient of a scalar function, and we call this scalar function V, and it is called the electrical potential, as we're going to explain soon. And we have a negative sign. The negative sign is mainly to indicate that the electric potential increases when we are going against the field. So if the field is caused by a positive charge, the closer we get to the positive charge, the increase the electrical potential it will be. Okay, so why do we need to do this? Why should we think about introducing a new quantity into the electrostatic field or into the science? The idea is that this quantity is a scalar quantity, and in many situations dealing with scalar quantity is easier than dealing with a vectorial quantity. Okay, so this is mathematically, the two sides of course mathematically equivalent. So now we can deal with the electric field, which is a vector, or we can deal with the electrical potential, which is a scalar. So what is the physical meaning of the electrical potential? So F equal QE and the work equal F dot dl, which is Q E dot dl. So E dot dl is the work done per unit charge. Per unit charge means for a positive charge of one column. This is the meaning of the electric potential, or E dot dl. So applying this concept, E dot dl from point 1 to point 2, mathematically you can prove this is V2 minus V1. So let us go with this expression. E dot dl with a negative sign here. So electric field minus electric field, it will be gradient of V. So gradient of V dot dl, if you go back and review the last lecture of the vector algebra when we talked about the physical meaning of the gradient function, when it is dot product with a unit vector or with a vector, it means that the change of potential along this line, which is delta V. So V here is not the volume, V here is the electric potential. So divergence, gradient of potential dot dl is the potential difference along the length dl. When we integrate this along any path between point 1 and point 2, this is the potential difference between the 2 points. So this is the introduction of a new quantity, which is the electrical potential, and the mathematical meaning and physical meaning of this quantity that we just introduced. So as I said, minus E dot dl from point 1 to point 2 is the potential difference between point 2 and point 1. So the potential difference is conservative. Conservative means the integration is independent of the path. So we go from point 1 to point 2. If we go in a straight line, we go in a whatever line, whatever path, it will be the same. So that's why we are saying the potential function is conservative. Also, from the property or from this the introduction of this electric potential function or quantity, we can prove that the field lines is always perpendicular to the surface of constant potential. Why is that? So we need to think about this. So if this line here is a line of equipotential line, which means any point on this line is having the same potential. We are saying if this is the case, the electric field must be normal to this line. Why is that? Okay, if we have this point here on the line and this point here on the line and they are very close, let us assume this distance here is delta L. Okay, we know that the potential here and here is the same. So if we integrated E dot dl along this path, the potential, the difference must be zero. E dot dl along this path must be zero. Why? Because this point and that point does have the same potential. So if E dot dl must always equal zero, the only way for this to happen is to have the electric field perpendicular to delta L, because now we are taking delta L along the line of equipotential or along the surface of equipotential. So this is a proof that the electric field must be perpendicular to the line of equipotential or the surface of equipotential. So far we are talking about the relative electric potential or the electric potential difference. Is there a formula or a value or like a definition for absolute electric potential? The answer is yes. So scientists agreed that we will consider the electric potential at infinity to equal zero. So this is the absolute point, and based on that we can find the absolute electric potential for any point as the potential difference between the point and infinity. So now let us go into more details. Let us talk about the electric potential because of a point charge. Again, we want to reach the case of charge distribution, electric potential due to charge distribution. We start by the simplest case, a point charge at the origin, and then we want to find the electric potential at any point that is like r distance from this point charge. So the potential difference of this point equals the potential difference of the point minus zero, which is the potential at infinity. According to this definition, it is equal to the integration from infinity to r, so with a negative sign, E dot dl. The electric field for this point charge, as we found out from the previous lecture, does have this expression here. It is along AR from origin to the observation point, Q the point charge, 4 pi epsilon naught R squares the distance between the observation point and the origin, dot dl. So dl, we are moving here to infinity along the field line, along AR. So dl equal, it is in the direction of AR, its value is dr. When we integrate this, we'll have this expression. We substitute with the limit of the integration. We'll find that the absolute potential of a point B, because of a point charge Q at the origin, equal Q over 4 pi epsilon naught R. R is the distance between the point charge and the observation point. So if we want to find the potential difference between any two points, 1 and 2, V1, 2 is V1 minus V2, and it will have this expression. We can now recall our information about the symmetry of the electric field. From that also, we can conclude that the electric potential is also having a spherical symmetry because of this setup. It's just a point charge, so all the points at a distance r from this point charge does have the same potential. So any surface of a sphere that has the center at the point charge will be a surface of equipotential. A surface of equipotential means that the electric field is perpendicular to that surface, which is what we found out in the previous lecture. The electric field is in the AR direction, which is normal to the surface of a sphere. So now if we have multiple point charges, if we have like discrete charge distribution in our problem, the electric potential of this collection of charges at any arbitrary point is the superposition of the electric potential caused by each individual charge. So it's very similar to this expression that we used for calculating the electric field because of a summation of point charges. So the electric potential because of a collection of point charges equal the sum, and here this sum is a scalar summation, regular summation, algebraic summation, because this is a scalar, not a vector, and this is one way of simplification. And the value is 1 over 4 pi epsilon naught, a constant. The summation is the point charge divided by r, the position vector of the observation point, minus rk prime, which is the position vector of the point charge. So it's very similar to what we used for calculating the electric field, but here we used like a vectorial summation for electric field. For electric potential, we are using scalar summation. Let us revisit the problem of electric dipole and calculate the electric potential because of this dipole. From the electric potential, later on, we're going to calculate the electric field. We know that the electric field equal minus gradient of the electric potential. So what is the electric potential for the dipole? It's at any observation point, and we choose, you remember that we choose the observation point to be far from the dipole. Far means that the distance from origin to the observation point is much larger than the separation between the 2 points, the 2 charges of the electric dipole, and much larger means it's 10 times or more larger than d. So r is larger than or equal to or larger than 10d. So writing the expression, the electric potential at the observation point equal q over 4 by epsilon naught r plus the distance from the positive charge to the observation point minus 1 over r minus. This minus is because the charge here is negative. From the geometry, we can say that r plus equal r minus d over 2 cosine theta. So if we have here, we just do this is supposed to be a perpendicular line. Let me draw it again. Okay, so if we go from this point, here, so r prime, which is this r positive, which is this distance, it will equal r, which is this distance minus this part here. So this part here equal d over 2 multiplied by cosine this angle. Okay, so r plus equal r minus d over 2 cosine theta, this angle, sorry. So cosine this angle to the minus 1. We can use Taylor series expansion to write it this way. So this is the first order approximation. We consider just two terms of the Taylor expansion. In the same way, 1 over r minus, it will equal this expression. So r minus is larger than r plus is smaller than r, and that's why we will find out here we have a different sign for 1 over r plus, 1 over r minus. When we take the difference, it will have this expression. Just substituting here, we'll find the potential of the arbitrary point to equal q d cosine theta divided by 4 pi epsilon r square. So qd is the magnitude of b. B is the polarization vector, if you remember, and because of the cosine theta is this angle. So cosine theta is b dot ar. So b qd equal b as a magnitude, and its direction is in the z direction. b dot ar will cause, or will give us b as magnitude cosine theta, which is the numerator here. So we have now the general expression for the electric potential because of an electric dipole. Now we need to find the electric field. So the electric field equal minus gradient of V. This expression here is like spherical expression in spherical coordinate system. We just apply the gradient in spherical coordinate system, and we have no dependency on phi. We just have dependency on r, we have dependency on theta, and we have two components, ar and a theta, which is the same expression that we had reached in the previous lecture using the vectorial summation of the electric field because of positive charge plus the electric field because of the negative charge. So this is another way of solving the same problem, and here we are showing the field lines between the positive charge and negative charge, and we have the equipotential surface, which are those red dotted lines. So those lines, you will find that the electric field always perpendicular to those lines of equipotential, and actually those are not just lines, it's surfaces. So if we just rotate, you will find, so this is a surface, but we are taking just a cut, cross section, and this is the equipotential lines. So this line here is an equipotential, this surface here is an equipotential surface. This is the equipotential surface of 0 because of symmetry, and you will find that all the fields must be normal to this surface that is midway between the positive charge and negative charge. Just a reminder, anytime you find like an assignment inside the lecture, it means that I recommend and advise you to solve this example from the book to gain more like skills in solving electrostatic field problems. So we have an example here. It is required from us to obtain a formula for the electric field intensity on the axis of a circular disk of radius b that carries a uniform surface charge density rho s, which is coulomb per meter square. So the first thing we think about drawing the problem or sketch of the problem, and second thing, choose the coordinate system. So here we have a disk, so we would go with a cylindrical coordinate system. So this is the sketch of the problem. We have a disk. We can put this disk on the xy plane. This disk is charged with surface charge density rho s, and we want to find the electric field on the axis of this disk. So we can choose any point on the axis. This point is 0, 0, and z, and we want to find the electric field at this point because of the surface charge distribution on this disk that does have a radius of b. So we can just like write it first as a summation, or we can go directly as like an integration. So we choose to solve this problem with v first, then apply the negative gradient of v. So v equal 1 over 4 by epsilon naught, then the summation over the available point charges of point charge divided by the distance from point charge to the observation point. Okay, so now to solve this problem, we're gonna divide this disk into differential surface elements and deal with every differential surface element like this one as a point charge. The charge in this surface element equal rho s multiplied by the area. The area, as we discussed in the lecture of orthogonal coordinate system, equal r prime d phi prime multiplied by r prime. Anything related to the source would have a prime indicator. So dq or qk, which will be substituted here, equal rho s multiplied by ds. So this expression here is a scalar summation. R is the position vector of the observation point, which is in the z direction. R prime is the observation point of the source, which is ar prime, r prime. So this is the observation point to the differential element. The magnitude equal z square plus r prime square. So the electric potential at the observation point, because of this surface charge distribution, equals the integration over the surface. So we are integrating over r and integrating over phi. So integrate over phi from 0 to 2 pi, for r from 0 to b. So just substituting here, q, which is qk, which is rho s r prime d phi dr prime, and the distance does have this expression, and we can solve this problem easily because r prime dr, which is 0.5 dr square. So we can solve this integration. Integrating first with respect to r prime, we get this. Then we integrate with respect to phi, which is gonna give us like 2 pi. 2 pi from the phi integration will go with this 2 pi, and we are left with this integration. Sorry, with this value here. So when r equals 0, we have the absolute value of z. Okay? Once we have this expression, then we can calculate E, which is minus gradient of V, and this is a cylindrical coordinate system. We substitute the definition or the expression for cylindrical coordinate system gradient. So no dependence on R, no dependence on phi, we just have dependence on Z. Then we have the expression. We can always expect that the electric field would be in the Z, along the Z axis, will be along the Z axis because of the symmetry, would cancel any R or phi component. So just I'm adding here a note that this same problem can be solved by the vector integral of the electric field due to differential surface charge element, and it will be like integral summation instead of scalar summation, or like a vectorial integration instead of a scalar integration. It would be a little bit longer, but it can be solved also using the electric field. So we're just like using the new things that we learned of calculating electric field by first calculating the electric potential, then applying the minus gradient function. Another example that I recommend you to solve it as like an exercise or part of your study. Okay, so far we studied 3 different ways to calculate the electric field because of charge distribution. The first method is the integration method. If we have like continuous charge distribution, volumetric charge, surface charge, linear charge, or like vectorial summation if we have like discrete point charges. This is method number 1. Method number 2, when we have symmetry, is by applying Gauss's law. We choose Gauss's surface where we have the electric field normal to the surface and uniform on it, so that we can use Gauss's law in solving those problems. So using Gauss's law is only useful when there is symmetry, but Gauss's law is always true. The last method that we learned today is using the electric potential method for summation, for integration. Then we apply minus gradient of the electric field. There will be a homework on this learning of the electrostatic field, and it's 1 week from the discussion session. As usual, at the end we are like I'm sharing the learning objectives, so that after like studying this lecture you can just review the main points and make sure that you understand them. Thanks everybody, and meet you in the discussion session.